This lecture is about the probabilistic topic models for topic mining and analysis. In this lecture, we're going to continue talking about the topic mining and analysis. We're going to introduce probabilistic topic models. So this is a slide that you have seen earlier, where we discussed the problems with using a term as a topic. So to solve these problems, intuitively, we need to use more words to describe a topic. And this would address the problem of lack of expressive power. When we have more words that we can use to describe a topic, we can describe complicated topics. To address the second problem, we need to introduce weights on words. This would allow us to distinguish subtle differences in topics and to introduce semantically related words in a fuzzy manner. Finally, to solve the problem of word ambiguity, we need to split an ambiguous word so that we can disambiguate its topic. It turns out that all these can be done by using a probabilistic topic model. And that's why we're going to spend a lot of lectures to talk about this topic. So the basic idea here is an improved representation of topic as a word distribution. So what you see now is the old representation where we represent each topic with just one word or one term or one phrase. But now we're going to use a word distribution to describe the topic. So here you see that for sports, we're going to use a word distribution over, theoretically speaking, all the words in our vocabulary. So for example, the high probability words here are sports, game, basketball, football, play, star, etc. These are sports-related terms. And of course, it would also give a non-zero probability to some other word like travel, which might be related to sports, but in general, not so much related to the topic. In general, we can imagine a non-zero probability for all the words, and some words that are non-relevant would have very, very small probabilities. And these probabilities would sum to 1. So that it forms a distribution of all the words. Now, intuitively, this distribution represents a topic in that if we sample words from the distribution, we tend to see words that are related to sports. You can also see it as a very special case if the probability mass is concentrated entirely on just one word, let's say sports. And this basically degenerates to the simple representation of a topic with just one word. But as a distribution, this topic representation can in general involve many words to describe a topic and can model subtle differences in semantics of a topic. Similarly, we can model travel and science with their respective distributions. So in the distribution for travel, we see top words like attraction, trip, flight, hotel, etc. Whereas in science, we see scientist, spaceship, telescope, or genomics, and science-related terms. Now, that doesn't mean sports-related terms will necessarily have zero probabilities for science. In general, we can imagine all these words will have non-zero probabilities. It's just that for a particular topic, some words will have very, very small probabilities. Now, you can also see there are some words that are shared by these topics. Well, when I say shared, it just means even with some probability threshold, you can still see one word to occur in multiple topics. In this case, I marked them in black. So you can see travel, for example, occurred in all the 3 topics here, but with different probabilities. It has the highest probability for the travel topic, 0.05, but with much smaller probabilities for sports and science, which makes sense. And similarly, you can see star also occurred in sports and science with reasonably high probabilities because they might be actually related to the 2 topics. So with this representation, it addresses the 3 problems that we mentioned earlier. First, it now uses multiple words to describe a topic, so it allows us to describe fairly complicated topics. Second, it assigns weights to terms, so now we can model subtle differences of semantics, and it can bring in related words together to model a topic. Third, because we have probabilities for the same word in different topics, we can disambiguate the sense of word in the text to decode its underlying topic. So we addressed all these three problems with this new way of representing a topic. So now, of course, our problem definition has been refined just slightly. The slide is very similar to what you have seen before, except that we have added refinement for what a topic is. So now each topic is a word distribution. And for each word distribution, we know that all the probabilities should sum to 1 over all the words in the vocabulary. So you see a constraint here. And we still have another constraint on the topic coverage, namely pi's. So all the pi sub ij's must sum to 1 for the same document. So how do we solve this problem? Well, let's look at this problem as a computation problem now. And so we clearly specify the input and output and illustrated it here on this slide. The input, of course, is our text data. C is the collection. But we also generally assume we know the number of topics, k, or we hypothesize a number and then try to mine k topics, even though we don't know the exact topics that exist in the collection. And V is the vocabulary set. It has a set of words that determines what units would be treated as the basic units for analysis. In most cases, we can use words as the basis for analysis, and that means each word is a unit. Now the output would consist of, as first, a set of topics represented by theta i's. Each theta I is a word distribution. And we also want to know the coverage of topics in each document, so that's the same pi ij's that you have seen before. So given a set of text data, we would like to compute all these distributions and all these coverages as you have seen on this slide. Now, of course, there may be many different ways of solving this problem. Indeed, you can write a heuristic program to solve this problem. But here we're going to introduce a general way of solving this problem called a generative model. And this is, in fact, a very general idea, and it's a principled way of using statistical modeling to solve text mining problems. And here I dimmed the picture that you have seen before in order to show the generation process. So the idea of this approach is actually to first design a model for our data. So we design a probabilistic model to model how the data are generated. Of course, this is based on our assumption. The actual data aren't necessarily generated in this way. So that would give us a probability distribution of the data that you are seeing on this slide, given a particular model and parameters that are denoted by lambda. So this capital lambda actually consists of all the parameters that we're interested in, and these parameters in general will control the behavior of the probabilistic model, meaning that if you set these parameters to different values, and it will give some data points higher probabilities than others. Now in this case, of course, for our text mining problem, or more precisely topic mining problem, we have the following parameters. First, we have theta i's, each is a word distribution. And then we have a set of pi's for each document. And since we have n documents, so we have n sets of pi's. And in each set, all the pi values will sum to 1. So this is to say that we first pretend that we already have these word distributions and the coverage numbers. And then we're going to see how we can generate data by using such distributions. So how do we model the data in this way? And we assume the data are actually samples drawn from such a model that depends on these parameters. Now, one interesting question here is to think about how many parameters are there in total. Now, obviously, we can already see n multiplied by k parameters for pi's. We also see k theta i's, but each theta I is actually a set of probability values, right? It's a distribution over words. So I leave this as an exercise for you to figure out exactly how many parameters there are here. Now, once we set up the model, then we can fit the model to our data. meaning that we can estimate the parameters or infer the parameters based on the data. In other words, we would like to adjust these parameter values until we give our data set the maximum probability. I just said that depending on the parameter values, some data points will have higher probabilities than others. What we are interested in here is what parameter values will give our data set the highest probability. So I also illustrated the problem with a picture that you see here. On the x-axis, I just illustrate lambda, the parameters, as a one-dimensional variable. It's oversimplification, obviously, but it suffices to show the idea. And the y-axis shows the probability of the data observed. This probability obviously depends on the setting of lambda. So that's why it varies as you change the value of lambda. What we are interested in here is to find the lambda star that would maximize the probability of the observed data. So this would be then our estimate of the parameters. And these parameters, note that, are precisely what we hope to discover from text data. So we would treat these parameters as actually the outcome or the output of the data mining algorithm. So this is the general idea of using a generative model for text mining. First, we design a model with some parameters that we are interested in, and then we model the data, we adjust the parameters to fit the data as well as we can. After we have fit the data, then we will recover some parameter values. We'll get the specific parameter values, and those will be the output of the algorithm. And we treat those as actually the discovered knowledge from text data. By varying the model, of course, we can discover different knowledge. So to summarize, we introduced a new way of representing topic, namely representing it as word distribution. And this has the advantage of using multiple words to describe a complicated topic. It also allows us to assign weights on words, so we can model subtle variations of semantics. We talked about the task of topic mining and analysis when we define a topic as a distribution. So the input is a collection of text articles, the number of topics, and a vocabulary set. And the output is a set of topics. Each is a word distribution. And also the coverage of all the topics in each document. And these are formally represented by theta i's and pi i's. And we have two constraints here for these parameters. The first is the constraint on the word distributions. In each word distribution, the probabilities on all the words must sum to 1 over all the words in the vocabulary. The second constraint is on the topic coverage in each document. A document is not allowed to cover a topic outside the set of topics that we are discovering. So the coverage of each of these key topics would sum to 1 for a document. We also introduced the general idea of using a generative model for text mining. And the idea here is to first design a model to model the generation of data. We simply assume the data are generated in this way. And inside the model, we'll embed some parameters that we're interested in, denoted by lambda. And then we can infer the most likely parameter values, lambda star, given a particular data set. And we can then take the lambda star as the knowledge discovered from the text for our problem. And we can adjust the design of the model and the parameters to discover various kinds of knowledge from text, as you will see later in the other lectures.